Hey guys, Mr. McKinney here, just going over some applications of position, velocity, and acceleration. So whenever you see PVA, that's me referring to position and velocity and acceleration. Now, we talked a little bit about position, velocity, and acceleration last semester, and we talked about how if you take the derivative, you'll be going down a level. So if we take the derivative with respect to time of position, we get velocity. If we take the derivative of velocity with respect to time, we get acceleration. So now that we're in the second half of calculus, we're not dealing with derivatives as much as we are dealing with integrals. So while derivatives will let you go down a level, integrals will let you move up a level. The primary focus of this video will be talking about displacement versus total distance. Now, displacement and distance both have to do with position, but the way we're going to find them in this video is going to be with reference to the velocity function. So if we have a velocity function and we want to find either displacement or total distance, we're going to integrate to go from velocity up a level to position. If we do the integral of just velocity, that will be displacement. That's basically the net distance traveled. If we do the integral of the absolute value of velocity, then it will get the total distance traveled. It'll take the area, whether it's above the axis or below the axis, and make it positive. So whether we're moving in the positive direction or the negative direction, we're going to count that distance. The displacement, the positive and negative, will cancel each other out. Just a couple of side notes. When we talk about speed, we're talking about velocity, but speed is always positive, so it's the absolute value. The AP exam likes to ask about whether you're speeding up or slowing down. Make sure you look at both the acceleration and the velocity to see if something is speeding up or slowing down. So for this video, we're going to be focused on this position function. So the position is equal to 3x sine of 2x. All right, the first thing we want to do is find the velocity function. So to find the velocity function from the position function, we would take the derivative. In this case, we have two functions, so we're going to need to use the product rule. So I'm going to have the derivative of 3x, which is 3 times sine of 2x, plus 3x times the derivative of sine of 2x. So the derivative of sine is going to be cosine of 2x, and then chain rule, derivative of 2x is 2. So I can make this all together be 6x cosine of 2x. So in order to find the displacement or the total distance, we're going to use the integral of velocity to move up a level. So for displacement, I would do the integral from 0 to 10 of v of t dt. And for the total distance traveled, it's very similar. I'm still doing the integral from 0 to 10. This time we're going to do the absolute value of velocity with respect to time. Now we're going to do all of this on the calculator, and I'm going to show you guys that on the next slide. But this is how we set it up. And on the AP exam, if you're on the calculator portion, this is all you need to show in terms of work. And then you can just write equal to whatever the answer is. But you do need to show what you're doing. You don't need to write down math 9 anywhere, but you need to show what you calculated. Now, let's take a look at what the calculator would give us for each of these. So for the integral from 0 to 10 of velocity, and I put my velocity function into y2, I would get 27.388, and for the total distance, a much larger number, 198.603, because I put the absolute value around the velocity. Now notice that I let the calculator do all of this for me. So I put my original function into y1, and then in y2, I can either take the velocity function by hand and put it in here, or I also showed the way that you can trick your calculator into doing it. So you don't have to type it in by hand. You can do the derivative of a function, and if you say x is equal to x, that will do the derivative everywhere. So you can just put this into y2, and that will do the exact same thing. Now up here I have a Desmos graph, so I don't actually have the position function. I have the derivative of the position function. And if I take the area underneath this velocity function, that'll tell me the distance, because I'm integrating velocity, so I'm going up. Now, right now I have positive and negative distances. So those are going to cancel out a little bit, which is why the displacement is only 27. When I do total distance, I'm going to be taking all of these areas and making them positive, which is why my total distance traveled is a lot more. this would be moving in the positive direction, this would be moving in the negative direction. So for displacement, they're going to cancel each other out. For total distance, basically all of these get moved up to the top and all the area ends up being positive. Again, we're just integrating velocity to get our position because we're undoing the derivative. All right, let's look at a couple other examples with this same function. So I've got my original position function, and now I've got my velocity function up here. The first question is the particle speeding up or slowing down at t equals 5? Now, we definitely need to look at acceleration because that's telling us how our velocity is changing. So acceleration is going to be the derivative of velocity. Now, at this point, I would have three terms because I'd take the derivative here, but when I take the derivative here, I'd have to use the product rule again. Since I'm on the calculator portion, I'm just going to let the calculator do that for me. So I just need to figure out what a of 5 is. Now, when you look at speeding up or slowing down, you also need to look at v of 5. So we're going to look at both of those on the calculator and just look for if they have the same sign or if they have different signs. If they have the same sign, they're speeding up. If they have different signs, they're slowing down. These other two are just kind of random topics that I wanted to tie in here. So average rate of change versus average value. Average rate of change, whenever you see average rate of change, that's a slope calculation. So y2 minus y1 over x2 minus x1. And you do the average rate of change, you do the slope calculation on whatever function they give you. So don't take the derivative first. The slope calculation is essentially taking the derivative. It's just an average rate of change instead of an instantaneous rate of change. So in this case, I would put in the position at 10 minus the position at 0 over 10 minus 0. And we're going to let our calculator do it for you. Now, for average value of a function, we use a different formula. So average value of the velocity function, the formula for average value is 1 over b minus a times the integral from a to b of whatever your function is. In this case, we're going to be finding the average value of velocity for the first 10 seconds. So 1 over 10 minus 0 times the integral from 0 to 10. We want the average of velocity, so that's the function that I'm going to put in here. And then again, we're going to let our calculator do it all for us. So put the functions into your calculator and then let your calculator do everything else for you. Average rate of change is a slope. Average value is not a slope, it's a fraction times an integral. Now the integral will give you your area, and you're basically dividing your area by your width to find the average height. Now if we think about it, the rate of change of position is velocity. So we're actually finding average velocity. We're finding the same thing on both problems. And if we look at the answer is the same because we calculated the same thing. Now again, instead of s of 10 minus s of 0, I have y1 because I had put s into the calculator in y1. And over here, I have my velocity put in as y2. Now backing up to look at if it's speeding up or slowing down, y2, that was my velocity, so v of 5 is negative. The derivative of y2 at 5, that's my acceleration. So because my velocity is negative and my acceleration is positive, the particle is slowing down because a of 5 and v of 5 have different signs. And then for average rate of change, slope calculation, average value, we use the integral and then we divide by the width. But in this case, we were calculating the same thing, the average velocity, which is why we got the same thing. So again, for speeding up and slowing down, make sure you look at both acceleration and velocity. The AP exam almost always picks one with negative velocity so that it does the opposite of what you think it would if you only looked at acceleration. So look at acceleration and velocity. If they have the same sign, it's speeding up. If they have different signs, it's slowing down. It doesn't matter whether they're positive or negative. Hope this was helpful. Have a great day.